Okay, today I'd like to give a presentation about the implementation of turbo code in AWGN channel. Let's first introduce the background of turbo code. The turbo code are a class of high performance forward error correction codes developed in 1993. And it is, of course, now widely used in 3G communication standards and also the satellite communications. And also in HSPA and LTE standards, turbo code is also used for the communication systems. And nowadays, the turbo code is competing with LDPC codes. These two schemes have similar performance, and the choice of between these two is a big issue when designing the communication system. Let's first see the system model. This flowchart is very familiar to us, and the sender want to send message to the receiver, and first the message should pass through the transmitter, which include the encoder, and then the message is converted to signal, and after modulation and transmission, the receiver receives the signal and by decoder to transform back to the message. Of course, in this model, the security issue is not included, and of course, it's not what we will talk in this presentation. And the turbo code is a forward error correction coder. The block consists of the scheme of turbo code consists of encoder and decoder. Both blocks, what we can see here, included in transmitter and receiver. Let's first see the turbo code encoder. Turbo code used RSC encoder, which is short for the recursive systematic convolution codes. And by the name, we could know that this scheme of encoder has recursive architecture, which means when the sequence pass through the block of RSC encoder, what we can see here in the chart, the D of n, the sequence Dn is passed through the RSC1 and RSC2. When passed through these blocks, the sequence will divide in two parts. The first part will directly directly to the output, and the other part will have pass the recursive architecture, which means the output will feed back to the input to join the encode. So the block of RSC encoder can be considered as an impulse response filter, and of course the filter has transfer functions. Okay, next let's talk about the turbo code decoder. For the turbo code, the several algorithms can support this decoder. Let's talk about the most widely used algorithm. The first one is Weiye algorithm, which is the algorithm used in UTMS, which is the mobile cellular communication standard in the third generation. And in that system, the turbo code decoder is called SOVA decoder, which is short for soft output Weiye algorithm, which outcomes the shortcomings of Weiye algorithms. Since Weiye algorithm have two shortcomings, the first one is the burst of bits. Since the turbo code is the forward error correction code, which is mainly focused on reduce burst of bits, but the Weiye algorithms will during this process will produce the burst of bits, so it will degrade performance. But in the soft output decoder, this shortcomings has been overcome. What we what the algorithm we talk about today in this presentation is mainly about the BCJR algorithms, which is short. The name BCJR is short for the developer of the algorithm, the name of developers for the algorithm. BCJR algorithms improved MAP algorithm by reducing complexity, which means BCJR algorithm is a log MAP algorithm. It used the log operation to transform the multiply operation to the adding operation, and then the complexity will much reduced. These are the two shortcomings we talked about earlier: the burst of bit errors and hard decision. Now let's talk about the interleaver. Let's back to the turbo code encoder. Here we have a block named pi of n, which is the position of this part. This part, the main task of this part is to permute the sequence in a random order, which means that the input to RSC2 is different and is independent from the input to RSC1. Then the code word of CP2 is different from CP1. This scheme has advantage. The same input sequence will produce the totally different code words, and for the communication system is a big advantage. Okay, let's see the scheme of interleaver. For the upper part, we have F1, 2, 3, 4, 5, 6, 7. And after interleaving, the sequence order becomes 3, 7, 1, 2, 6, 4, 5. which is totally random order. They can be the other order, not this is not a particular part, unique part. It's just a random chose from the totally random order. Okay, let's talk about the channel model. Here we simulate the performance of turbo code. We just use the AWGN model, which is short for additive white Gaussian noise channel, which means this channel just have additive noise. It doesn't have the fading or interference or other factors may affect the performance of turbo code. Here is the result of turbo decoder simulation. And now I run the code again and let's see it on the MATLAB. Okay, here is the result, and we can see that the blue line is the theoretical bound, and after the first iteration, the performance is not that good. The curve is very closely to the bound, but after the second iteration and the third iteration, the BER value decrease very quick as the SNR increase, which means that the architecture of the decoder used iteration architecture is worked because after each iteration the performance become better and it proved the function of the iteration. Okay, the turbo code is, of course, is widely used in the third generation's communication standards, the UTMS, HSPA, LTE. All these standards will use turbo code as the coding scheme, and for the conclusion, as we see in the simulation result, the iteration architecture is a big advantage of the turbo code decoder, which result in the better performance after each iteration. But on the other hand, the turbo code system is parameter sensitive. Here we just used the additive Gaussian noise. If other kind of channel join the communication system, the turbo code may not perform that good, and it needs the better may need to be improved in that case. Okay, that's all. Thank you very much. Thank you.